Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussion related to this particular course, ESE 201, Introduction to Electronics. This is lecture number 5, and we continue our discussions related to methods for circuit analysis. We said that like any discipline, we require tools for analysis, and today we'll look at two tools. One of them is what we call as a nodal method of analysis, and the other one is mesh method of analysis. So we'll add two tools to our toolbox, which will help us in future in analysis of circuits. Okay, so the goal of analysis of circuits is to understand the circuit, which would help us then in designing it, modifying it. So that's the larger goal of circuit analysis. And to help with that particular process, we need to find voltages, currents, and power in the circuit. And note that if you calculate voltage and current, then of course power can be easily determined. Power is voltage into current, so it's not an independent quantity. Once you know voltage and current, power can be determined. The other one is if you determine the voltages, let's say everywhere in the circuit, we'll elaborate on that. Then you can determine the currents also. So voltage and currents are not really independent of each other. If you determine all the voltages, then you'll be able to determine all the currents as well. On the other hand, if you're able to determine all the currents, then you can determine the voltages also using the models of circuit elements. So let's elaborate on that. Let's take a circuit like this, given circuit here. And let's say, you're able to determine all the voltages that are there in the circuit. Voltage at this node, voltage at this node, voltage at this node. So there are 3 nodes here. The other one is a reference node. So suppose you're able to determine V1, V2, V3. So what we are saying is that if you determine V1, V2, V3, you can determine everything else in the circuit. For example, you may be interested in this particular current, I2, let's say. Well, I2 we can determine as V1 minus V2 into I2 into R2. So what did we use? We have these voltages here, and we have the model of this particular element. In this case, it's a resistor, so we use the Ohm's law. If there had been some other element, we would have used the model of that particular element to obtain the model gives us a relationship between current and voltage. So we already know the voltage across that particular element, and so from the model, we would have obtained the current here. So if you determine all these node voltages that are there, you know everything about the circuit in terms of the currents and power that are there. Similarly, for example, if let's say by some method, if I determine all these currents, I1, I2, I3, I4, I5, if I determine all the currents, then we are saying, well, you can determine everything else in the circuit. For example, you may be interested in knowing the voltage here, right? So you may be interested in knowing, let's say, what is the voltage at V1 at this particular point. Well, so we know V1 minus V2 is I2 into R2, right? So now to determine V1, we have to know V2. And so V2 we can write as V2 minus 0 volt equal to I4 into R4. Since we already know I4, we know R4, so we'll determine V2. And then we plug it here, and then we'll know V1 here. So again, if you determine all these branch currents that you see here, in every branch, you're able to determine current, then you'll be able to determine voltages everywhere in the circuit. And once you know voltages everywhere in the circuit, currents everywhere in the circuit, then you have all the information about the circuit that is there here. So in the first method, what we will do is we'll look at a method which allows us to calculate all the voltages in the circuit, right? So we said that once you determine all the voltages, you will know everything else about the circuit here. So in nodal analysis, the variables used to describe the circuit will be node voltages. And node voltages, we will define a reference node in a circuit. So node voltages will all be with respect to that reference node here. And so that's okay. Usually the reference node is, sometimes you have a choice. Sometimes the reference node is given in the circuit. There is an explicit ground connection that is there here. At other times you have a choice of using the reference node, and the choice can help in simplifying the circuit. As I said, the reference node, you can take it as 0 volts, and we can term it as ground here. All right, so let's look at this particular circuit here. So in this case, the nodal, so these are the nodes here, here, and here, and we have taken the reference node as ground. And nodal method will give us the voltages V1, V2, and V3, right? So how do we do that? How do we, how do we go about this process of getting the values of these voltages, these nodes here? So the first step is, given any circuit, identify and number the nodes and choose one as a reference node, right? So that's the first step. Given a circuit, for example, a circuit like this, and so what you should do is identify all the nodes here. So these are the nodes here. Nodes is a place where we have two or more elements are joined together here. So this is a node, this is a node here, this is a node here, and this is a node here. So we identify 4 nodes, number them up. 1, 2, 3, and 4. In whichever way you want, you number them up. So we have 4 nodes here, right? So that's the first step. Choose one as a reference node. So we have a choice here, and we choose this one as a reference node. We put it as ground, and we do that. We could have chosen 3, we could have chosen 2, we could have chosen 1 also. We choose 4 here because note that what we are trying to determine is all the node voltages. So when we choose 4 as a ground, this node becomes 0 volt, so we don't have to determine its voltage. And not only that, node 1 we immediately know its value because this is a voltage source, so node 1 is also Vs. So that reduces 2 unknowns in the circuit, the value of the voltage at 2 and the value of the voltage at 3, right? So that helps us. The choice of the ground here helps us in reducing the number of unknowns in the circuit here. The next thing is, at each one of these nodes, the unknown nodes here, we write down the KCL. So we have 2 unknown nodes here. So we write down KCL at node 2. So KCL at node 2, so the current entering this node 2 from this side, V1 minus V2 by R2 is 1 current. Current entering from this side, let's say from here, would be 0 minus V2 by R4. And the current coming from the right hand side will be V3 minus V2 by R3. And sum of all these currents entering the node equal to 0 here. So that gives us one equation when we write it at 2. Similarly, we can write it at 3. So current coming from the left, V2 minus V3 by R3. So that's one current. Current coming from the bottom, 0 minus V3 by R5. And then current coming from the top, which will be V1 minus V3 by R1 here. So that's another equation. So we have this equation here, and we already know V1 equal to Vs. So value of V1 is known. So we basically have 2 unknowns here, V2 and V3, 2 unknowns here, and we have 2 equations, and we can solve them. Solution of these equations will give us the values of the node voltages that are there in the circuit, right? So that's a well-defined systematic method of identifying the nodes, numbering them up, choosing a reference, and then writing KCL at these nodes here to generate equations which upon solution will give you the values of the unknown node voltages here. Right, so it's a systematic method for transform. We said analysis of circuits is basically taking a circuit and transforming it into a set of equations. And then it becomes more of a math problem. You solve those equations to get the answers that you're looking for. So this is what we have done using the nodal method. Given a circuit, we have a systematic method of transforming it into the system of equations. And then, of course, so the whole process is actually very routine, very well defined, and there's a well-defined algorithm, and it can be readily automated by a computer program, and we call that as a circuit simulator. At the end of this particular lecture, we'll see how that circuit simulator is able to, an example of circuit simulator. All right, so transformation of circuit into equations. That's what is the first step in analysis, and the nodal method allows us to do that in a very well-defined manner here. So let's take an example, a concrete example, and work it out. So we have given a circuit like this. And so first step, remember, we identify all the nodes. So 1, 2, 3, 4, here, 4 nodes here, and we number them up and we choose 1 as a reference node. So again, we choose this as a reference node. This becomes ground, and the value of this node then becomes 10 volt here. So that makes it easy. And we number them up 1, 2, 3. There's no need to number the ground node here. You could take it as 0, let's say. And so we write at KCL at node 1. So we find out all the currents entering the node 1. We sum them up to be equal to 0. So there's 1 ampere entering from here. Then there is a V2 minus V1 by 5 entering from left here. And then from the top, there's a current V3 minus V1 by 15 equal to 0 here. So that's, we write KCL at node 1. We can write KCL at node 3 here. So this is the current coming from the bottom, 0 minus V3 by 10. Current coming from the left here, V2 minus V3 by 5. And then current coming from the top here, so V1 minus V3 by 15. And we already know V2 equal to 10 volt. If this is 0, then this is 10 volt here. So we have basically two unknowns here. We don't know what is V1 and what is V3. And we have two equations, and we can solve them up to get the answer. So I'm not going to go through the process of algebra here. V3 equal to 7.857 and V1 is 13.2. So we get these two values here, and V2 we already know. So if our interest is in finding out what is IS, then IS, if you write KCL at node 2, so IS will be equal to current going left and current going right here, sum of those two currents. So V2 minus V1 by 5 and V2 minus V3 by 5. So we sum them up and we get minus 0.21 ampere here. So we see that given a circuit like this, how we can apply the nodal analysis method to arrive at the answers that we are looking at. And so we have all the node voltages, and if you would like, what is the current going in 15 amperes, what is the current going in 10 amperes or in 10 ohms and 5 ohms. So you can get all of that very easily once you have all these voltages that are there here. So let's look at a case where we have a little bit of a complication where we have two voltage sources and one of them would be floating. So I'll explain in a minute what is floating. So as usual, if you want to analyze this particular circuit, what you would do is you would number all the nodes. So we identify all the nodes that are there here. And one of these nodes we are going to select as a reference node. So let's say, as usual, we select 4 as a reference node. So the moment we select 4 as a reference node, the value of this particular node is known here. And the value then becomes equal to the value of this voltage source, Vs1 here. Now, if you look at this voltage source versus this voltage source, so this one voltage source has one of its terminals which is grounded, right? And the other one is, gives us the value that is expected of Vs1. This particular voltage source has both the terminals which are, non-zero or non-grounded. And we call this voltage source as a floating voltage source, right? Floating in the sense that, when something is not grounded, the feet are not on the ground, then I guess you're floating, right? So in that sense, in 1 feet of this particular voltage source is grounded, and both the feet of this particular voltage source are up in the air, right? They're not on the ground. So in that sense, we call it a floating voltage source. So when we have a floating voltage source, we have a little bit of complication. So fine, we have identified all the nodes. Let's look into that. This one is ground. And so we write KCL. We write KCL at node number 2, let's say. Right? So we know node number 1, the voltage already here. So let's write KCL at node number 2. So if you want to write KCL at node number 2, you want to write all the currents entering that node here. So current entering from the left is fine, V1 minus V2 by R2. Current coming from the bottom is 0 minus V2 by R3. Well, what about the current coming from here? How do I write this up? What is the current coming from here? This is a voltage source. And the model of a voltage source is that V3 minus V2 is, or V2 minus V3 is Vs2. But we don't know what the current is. And for writing KCL, I need a current value here. So I'm unable to proceed and write a KCL at this particular node here. Similarly, if I write KCL at node 3, well, at node 3, the current coming from the top is V1 minus V3 by R1. The current coming from the bottom is 0 minus V3 by R4. And what is the current coming from the left here? Right, so we are unable to write. So we are not able to write the KCLs, and therefore we are not able to proceed. Of course, we know that V2 minus V3 is Vs2. And we also know V1 equal to Vs1. But note that the nodal analysis method works with node voltages. So, and it uses KCL. So we are unable to write KCL at this node. We are unable to write KCL at node number 3, and therefore we are not able to complete the equations and thereby solve those equations to arrive at the answer that we are looking for. So a way out, what we do is, one of the ways of doing it is, we combine these two nodes here. Node 2 and node 3 were problematic nodes for us. We combine them together into what we call, because it's a combination of two nodes, we call it a super node here. Node 2 and node 3 are merged together into a super node, and KCL is applied to the super node here. So to this combination of 2 and 3, we apply KCL to this surface here. So if we do that, again, sum of currents entering a super node is 0 here. So current coming from the left, V1 minus V2 by R2 here. Current coming from the bottom is 0 minus V2 by R3. Current coming from the bottom here to this side is 0 minus V3 by R4. And current coming from the top is V1 minus V3 by R1. So that becomes an equation. When you combine them together, this is the equation that we get. And of course, the super node is where, for example, there's a floating voltage source. So V2 minus V3 is Vs2 and V1 is Vs1. So now we have these equations together, and note that we have two unknowns basically, V2 and V3, and we have these equations, and we have two equations here, and these equations can be solved to get the answers that we're looking for. So if you do end up with this is a grounded source, so that doesn't cause a problem. In fact, a grounded source immediately yields the value of the other node. The floating voltage source, we know the relationship V2 minus V3, but we don't know what is V2, we don't know what is V3, and we are unable to write the current directly in our KCL. So we combine them together into a super node and then write equation for that super node here. And so that then enables us to transform the circuit into a system of equations and solve them up. All right, so let's look at the nodal analysis where we have a current source, and we have an independent current source and we have a dependent current source here. So this current is dependent on this particular value here. So that doesn't cause any problems for us. As usual, we define identify all the nodes. Let's take this as ground. So V2 becomes 10 volt here. And then let's write down the equation. KCL at node 1, current entering is 1 ampere from here. V2 minus V1 by 5 from right hand side. And from the top here, the current entering is 2I. So we leave it as 2 into I equal to 0. Then let's write it at KCL at node 3. So current coming from the bottom is 0 minus V3 by 10. Current coming from the left, V2 minus V3 by 5, and current coming is actually leaving this particular place here, so we put minus 2I equal to 0. So note that we want equations only in terms of node voltages. So we have an I here, but only temporarily. V2 equal to 10 volt. And then what we can do is this I that is here, we can write it as V3 minus V2 by 5. Right, so we have 5 here. So wherever you see I, you can go ahead and substitute this equation here and equation here. And eventually you end up with, there are two unknowns, node voltage here and node voltage here. And you end up with two equations and you can solve them to get the answer that you're looking for. So dependent current sources, you will see, do not cause any issues in terms of applying this particular method. The method is perfectly general. Well, let's look at a case where we have a dependent voltage source, and the dependent voltage source will make it floating by, again, identifying these nodes, taking it as ground. So this dependent voltage source becomes floating. And when we have a floating node, we use the concept of a super node here. So we'll combine them together into a super node. And then we write down equation at the super node. So you can verify V1 minus V2 by R2 here, 0 minus V2 by R3, current coming from the bottom here, current coming from the bottom here, and then current coming from the top here, V1 minus V3 by R1. And so that's there. And then V2 minus V3 is 0.5 Vx, and that is there here. And V1 minus V3 is Vx here, right? So what you can do is, V1 minus V3 is Vx, so you can take Vx and substitute it here in V2 minus V3, and so you again end up with two equations and only in terms of node voltages, and you can solve them to get the values that you're looking for. So V1 is already known, you'll get V2 and V3, and thereby you know everything else in the circuit, right? So that was the nodal method for analysis. And a complementary part is where we try to determine the currents instead of the voltages, is what we call as the mesh analysis. So in mesh analysis is another general purpose procedure where we use mesh currents as the circuit variables. So what exactly is a mesh? And we apply KVL. In the previous case, we applied KCL. In this case, we applied KVL. So a mesh is a loop which does not contain any other loops within it. All right. So let's see. So let's say we have a circuit. If you recall, this was a problem in homework assignment number 1. So whatever these elements are, let's not bother. So mesh is a loop which does not contain any other loop within it. So look for these loops here which have in simple terms, there's nothing inside that particular loop here. It's empty here. So look for these empty spaces here. So this one is a loop. And what we, it's a mesh. So what we do is with each mesh, we associate a current, right? So let's say there's a current flowing in this particular mesh here. This is another mesh. This is another mesh here with empty space here, surrounded by elements here. This is another mesh here, and there's another mesh here. So we have 1, 2, 3, 4 meshes here. Well, let's look at this particular circuit. In this case, we have this mesh, we have this mesh, and we have this mesh here. So the first step in mesh analysis is to identify all these meshes that are there and associate a current with each one of these mesh here. A current, let's say I1 flows through this mesh here, current I2 flows through this mesh here, and current I3 flows through this mesh here. Note that these are kind of a temporary. The actual current flowing through R2 is neither I2 nor I1. Right, so you can clearly see the current flowing through R2 will be I2 minus I1 here. So it's an intermediate variable. This mesh current here, we define it. We say there is a mesh and there's a current, assuming that there's a current, an imaginative, if you want to call it, a current circulating in this particular mesh, which is I2, and a current circulating in this mesh, which is I1, and a current circulating in this mesh, which is I3. So once you do that, the next thing we do is we write down Kirchhoff's voltage law for each mesh here. So let's take this mesh number 1. You could start from anywhere. So let's start from this particular one here. So when I go across it, let's look at the voltage drop. So there's a voltage drop I1 into R1. Fine. Then we come down here. And then we have to go here across R3. So what is the current flowing through R3? Well, I1 is causing a current to flow left, and this I3 is causing a current to flow right. So the net current flowing through R3 is I1 minus I3. And so the drop is I1 minus I3 into R3. So you come over here, and then you go across R2. So the net current flowing through R2 is I1 minus I2. That's a net current into R2. So that's equal to 0. The sum of the voltage drops across, in a loop in this particular mesh is equal to 0. So you write down KVL in this particular mesh here. Write down KVL in mesh number 2. So let's start from here. Let's start from here. So start from here. So there's minus Vs. There's a voltage gain here. Then the drop here across R2. So the net current will be I2 minus I1. So we go along the direction of the current that we have chosen, right? So the drop here will be I2 minus I1 into R2. Then we come here, and the drop is going to be, we are going from up to down here in the direction of the currents chosen here. And that would be equal to I2 minus I3 into R4. So we can choose a clockwise direction of currents, mesh currents everywhere to be consistent. Then mesh 3 we can do similarly. We could start, let's say, as I said, you could start from anywhere. Let's say you start from this particular point, so I3 into R5. Then you come here, and then you go up, and the net current flowing is, when you're going up, the drop is I3 minus I2 into R4. And then you're going right here. So the net current through this going right is I3 minus I1 into R3. And the sum of the voltage drops equal to 0. So the idea is that you identify all the meshes that are there, you associate currents with these mesh currents I1, I2, I3, and in each one of those meshes you write down KVL. And so we have three unknowns, I1, I2, I3, and we have three equations. So what we have done is we have transformed the circuit into a system of equations, and you can solve these three equations to get the mesh current. You will get I1, I2, I3, and note that once you get I1, I2, I3, you know all the branch currents. The moment you know I1, you know the current in R1. If you want current in R2, well, we already said current in I2 is going to be I1 minus I2. The current in R5 is going to be simply I3. The current in R3 is going to be I3 minus I1. And like that, you'll be able to get all the branch currents. And you want the voltages anywhere? Well, if you know all the currents in the branches, we've already said, you know apply Ohm's law here, and you can get all the voltages as well. So again, a very general method, but works on the basis of identifying meshes, associating mesh currents, applying KVL, and then solving the equations. So let's look at this example. So let's put in three meshes here. Let's call these currents I1, I2, I3 all clockwise here. And let's write down the equation. So for the first one, you can start from here, I1 into 15. There's only I1 current flowing through this, I1 into 15. Then you come here, you go clockwise. So you come here, the current is I1 minus I3. So you go in the direction of the current that you've chosen, I1 minus I3 into 5. And then we are moving like this here. We are going in this direction and measuring the drop here. So the net current is I1 minus I2 into 5 here. And like that, you can write for mesh 2. You don't even have to write, because note that I2 is equal to 1 ampere here. Right? So I2 equal to 1 ampere here. So that's straightforward. For mesh 3, similarly, we can write this equation here. And we can solve them up. And I'm not going to go through the maths here. So I1 will be 0.356 amperes here, and I3 is 0.78 amperes here. Right? So this compares the two methods here. In nodal analysis, same circuit. So this compares the two methods here. In nodal analysis, we identify the nodes, we choose a reference node, we solve for all the node voltages here. And once you get the node voltages here, you get the current that you want here, IS here. In this case, you identify all the meshes there, associate mesh currents I1, I2, I3, write the KVL, and you get all the mesh currents. And after that, the current that you're interested in, let's say IS, in this case will be I3 minus I2 equal to minus 0.21 amperes here. You get the same result. Both are very general methods. Same results you get from both of them. And we'll come back to which method to use in which situation. Sometimes it's obvious, sometimes both the methods are equivalent. All right. So just like nodal, if you have a current source, normally current source will not cause a problem, but if you have a current source which is common to two meshes, that may cause an issue between them. So let's look at it. Let's say you want to write, so three meshes are there. So three meshes are there, and we are write down the Kirchhoff's KVL in mesh number 1 is straightforward, so that's not a problem. In mesh number 2, let's write in mesh number 2, you start from here, so this minus 10 here, voltage gain, I2 minus I1 into 5 is 5 here, and then we come here, right? And note that we are writing KVL, so we need a voltage drop across the this current source here, and we don't know what to write here. So again, we get into a trouble. We are unable to complete the KVL equation here. Similarly, if we want to write it for this, if we start from here, let's say this I3 into 10, fine, but what is the drop here? We are unable to write, and here will be I3 minus I1 into 5. So we don't know while writing KVL what is the voltage drop across this particular, what to write in terms of voltage drop across this current source, which is shared between two meshes here, right? Which is common to two meshes here. So we are unable to write, so we are unable to proceed, and the procedure is the same. The procedure is the same. Note that if the current source which is at the boundary, which is shared between two meshes, which causes a problem. If we have a current source here which is not shared between two meshes, right? This particular branch is not shared here, then that doesn't cause a problem. In fact, it makes it easy. I2 is simply equal to 1 ampere here. But in this case, it causes a problem. We are unable to write the KVL for each one of those meshes. And the way to solve it is again the similar method as supernode. Here we call it super mesh. So we combine mesh number 2 and mesh number 3 into one single mesh. And because it's a combination of two meshes, we call it a super mesh. And we write down KVL for the super mesh. So for the first mesh, we write down the equation as it is, I1 into 15, I1 minus I3 into 5, and all that, the same way we write it. For the next case, we combine, we write it for a super mesh like this here. So let's do that. Let's start from here. So this is minus 10 voltage gain. Then we go across this 5 ohm resistor, the I2 minus I1 by 5 here. Then we come here and then we go here. So it is I3 minus I1 in this direction, I3 minus I1 into 5. And then down here is I3 into 10. And then we are back at the original point here. So we are able to write KVL for the super mesh here. And the other thing that we know is the relationship between I3 and I2. So note that I3 minus I2 is equal to 1. I3 is trying to force a current up, I2 is trying to force a current down, and the difference between the two will be the actual current, which is 1 ampere here. So we write this out. And now we have three unknowns, I1, I2, I3. We have three equations. You can solve them up and get the answers that you're looking for. So if you do end up with a current source which is shared by two meshes, then combine them up together into a super mesh. All right, so here is another example. So in this circuit, we have I1, I2, I3, I4. We have all these four meshes that are there. And for mesh number 3, no problem. You'll be able to write the KVL. Mesh number 4, you'll be able to write the KVL. But for I2, you would have a problem because of this current source. For I1 also, you have a problem because of this current source. So these two meshes share a current source. So combine them together into one super mesh. So what you do is you write down for mesh, this mesh, and this super mesh. And then use the relationship that I2 minus I1 will be equal to 5 amperes. And so you'll get your four equations. Two equations for these two meshes, one for the super mesh, and one for the relationship between I2 and I1 defined by 5 amperes. So you'll get four equations, solve them up, and you get the answers that you're looking for. In this case, we have a dependent current source, and this current source is shared between these two. This current source is shared between these two. So no problem in terms of writing KVL for this mesh. There'll be a problem in writing KVL for this mesh here because of this current source. There'll be a problem with writing here, and there'll be a problem with writing here. Now in this case, if I combine these two meshes, I solve the problem of not knowing the voltage across this particular one. But I still have, when I try to write KVL, what will I write the voltage drop across this current source? So this is still a problem. So what we can do is super meshes, not just two meshes combined together, but you can combine three meshes here. So we can combine these three meshes together and define and write it as a super mesh. So basically then we have sort of two KVLs to write, one for this and one for this super mesh. And note that for a super mesh, let's say we start from this ground terminal. So I2 into 6 here, then I1 into 2 here, then we go here, I3 into 4 here, then I3 minus I4. Note that this mesh is causing I3 and this is causing I4. So I3 minus I4 into 8, and we come back to ground. So that's for the super mesh here. And the other one is for this one here. And of course we have the other equations. We have I4 equal to minus I0 here. We have I2 minus I1. I2 minus I1 is 5 amperes here. And we have I3 minus I2 is 3 I0 here. So these current sources give us relationship between the mesh currents here and the mesh currents here. So we have enough equations. We can transform them now and solve them up to get the answers that we're looking for. Right, so as a summary, we have two very general methods, nodal analysis and mesh analysis. You can apply either one of them to get the answers that you're looking for. And in one case, we work with node voltages. In the other case, we work with mesh currents here. And if you solve using mesh analysis, well, you can get all the node voltages. If you solve using nodal analysis, you can get all the currents that are there here. So a question obviously arises is when we have two very general methods, which one to use and in which situation. So as a general thing, note that the choice of a method, one way of determining that is choose a method that will result in lesser number of unknowns and lesser number of equations to be solved. So choose nodal analysis for circuits with fewer unknown node voltages than unknown mesh currents. Similarly, and vice versa. Sometimes your interest is in a particular node voltage, so nodal analysis may make more sense, because otherwise if you determine the mesh currents, there's a little bit of step involved to determine the appropriate node voltage here. So look at this circuit here. In this circuit, for example, if I apply mesh, well, I will have I1, I2, I3, and I will have to solve three equations to determine I1, I2, I3. Well, if I take the same circuit and apply nodal, and these are my nodes here, and if I choose 4 as ground here, so node, in this case, node 1 is immediately known, is 15 volt. Node 3 is also known, which is 10 volt, and the only unknown node is node number 2. So I have to solve only one equation as compared to 3 equations here. So nodal analysis obviously makes sense here. Well, a complementary part of it, in this case, if I use a mesh analysis, well, if I use mesh analysis, I immediately know I2 is 1.5 amperes, I3 is -1 ampere, and only one unknown, which is I1. So I have to write only KVL here and one unknown, and I will get the answer immediately. If I apply the nodal analysis here, well, as usual, we do ground here. So I don't know what is V1, I don't know what is V2, I don't know what is V3. So we'll have to write KCL at each one of them and solve 3 equations. So it's obvious in this case, the mesh works better. In the other case, the nodal was working better here, right? So mesh analysis requires lesser number of equations to be solved here. Now, both methods are suitable for automated analysis. As I said, very general methods, very well-defined algorithm for finding the currents. And both can be used, and well, analysis for understanding, so we'll come to that. So let's, as I said, we'll wind up this particular discussion with showing you how the computer simulation of the circuit works. So we'll have more discussions related to that. So I'm taking a circuit simulator called MicroCap, and this was one of the circuits that we were thinking of. That is there here, one of the circuits that we discussed in our discussion here. And so this is just a figure, just a picture, and this is the circuit that I've drawn in the simulator. So you can pick up elements from a palette here and make the circuit. So it's the same circuit you can see here. And we go to analysis, we do dynamic DC, right? And it gives us all the node voltages. Note that 10 volt here, obviously 7.857 voltage here, 13.214 the voltage here. Well, if you're looking for currents, it gives me all the currents here. 642.85 milliamperes going right, 428.57, 785, 214. If you recall, if you go back to the discussion, we had a value of current flowing through this was 0.21 ampere here, so 214.286 milliampere here. Note that it gives you very precise answers and in almost no time. And if you're looking for, let's say, power, it gives you power dissipated in this resistor, in this resistor, in this resistor, and here. And this is a voltage source, so it gives power generated is negative here. Right, so if you're looking for voltages, if you're looking for currents, if you're looking for power and a lot more, you can readily make circuits in a simulator, and is using a method, I don't know exactly which one, but is using a method similar to the nodal or the mesh to generate a set of equations, solving it to give all the answers that you're looking for. And the issue, of course, arises that if the computer can give us all the quantities that we are looking for, then what exactly are we doing in terms of analysis? Well, the computer is giving us numbers, and that's where I wanted to end the course, end this particular lecture here. That analysis that we are doing is not just for computing the values of currents and voltages. That's a means for understanding the circuit. And we want to understand the circuit so that we can modify it, we can design it, and in that we can do analysis by hand. But we also use computers to check our analysis and as an aid in design work. So let's stop here.